Hello class, today we will be finishing up work and we will do the third situation, which situation is pumping liquid from a container. In the last portion, we covered the work done in stretching springs and also lifting objects of varying weight. So this is our third topic regarding work. Let's look at an animation. This represents a side view of a container that contains some liquid. And we're going to be pumping this liquid all to the same height somewhere above the container. Then we're going to slice through this liquid horizontally and then lift those slices one at a time to that height. Now, some things you notice here is that not every slice is going to have the same weight because the slices contain different amounts of water. Also, not every slice travels the same distance. The slices near the top travel a shorter distance than the slices toward the bottom of the container. We're going to find the work done in lifting each slice and then do an integral to add all those works to get a total amount of work done to remove all the liquid from the container. A rectangular tank is full of a liquid that has a mass density of 500 grams per cubic meter. That's a mass density. Notice that we're in the metric system. So we're going to want to do work in terms of joules, which means Newton meters, which means I'm going to have to convert kilograms to newtons at some point. The base of the tank is 2 meters by 3 meters and the tank is 4 meters tall. The liquid is pumped to a height of 3 meters above the tank. Find the total work done. Step number 1 is to draw a side view of the container and position the center of the bottom at the origin. Then draw an arbitrary horizontal slice. The container we're working with is rectangular. It's 3 by 2 by 4 meters. I'm going to look at it from this angle. So it's going to look like a rectangle. The next set of instructions were to position the center of the bottom of the container at the origin. And we're going to be pumping the liquid to a height that is 3 meters above the top. And this container is 4 meters tall. So we know a few things. We know that this height is y is equal to 4. And we want to go to a height that's 3 meters above that. So that's going to be y equals 7. Next was to draw an arbitrary horizontal slice. Also, this tank began full. So initially, it was completely full. So we need the water all to exit. I'm going to draw an arbitrary slice that's partway down this process of emptying like you saw in the animation a moment ago. Now this slice is currently at a height that is given by a y-coordinate. And the slices are going to vary from y equals 0 to y equals 4. Our initial slice is down here at y equals 0, and then the final slice of water is up here at 4. Or you can look at it backwards too. It doesn't matter if you think of the slices leaving from the top and working your way down, or if you remove the bottom slices first and then the top slices. Now that slice needs to travel this remaining distance to get to where we're pumping the liquid. So we also need to know how far this is. This is going to be the distance traveled by the slice. This whole gap here is 7, so therefore d is 7 minus y. Well, what does a slice actually look like if I were to draw it at an angle? Right? It would be a very skinny slice, something like this. Have a little bit of thickness. It always has a width of 3 meters, a depth of 2 meters, but the thickness is the change in y, the dy. Now this will be the same dimensions for every single slice in this case. So step 2 is going to be find the weight of the slice as a function of y. Well, since all of the slices are identical in this case, then it's going to be a constant function. Let's first write down what the volume of the slice is. Right? To find the volume of this box, you just multiply the 3 dimensions. Also, the dy is measured in meters. So we have 2 times 3 times dy, which is the same thing as 6 dy. This is meter time meter time meter. This is cubic meters. This is a volume. And the mass density is 500 kilograms per cubic meter. So if I want to find the mass of the slice, I would take its volume and multiply it by this 500 kilograms per cubic meter. So 6 times 500 is 3,000. Then we have the dy, and the units wind up being kilograms. Now I want to find the weight or the force of that slice. So the weight of the slice, if you know how many kilograms the mass of an object is, to find its weight, you multiply that by the gravitational constant, 9.8. This was discussed in the last lecture. So you would take this 3,000 dy kilograms, multiply it by 9.8 meters per second squared, is 29,400. We need that dy there, then newtons. As far as y is concerned, this expression is constant. Every single slice weighs 29,400 times dy newtons. Step 3, find the distance that the slice is lifted as a function of y. So that slice, which is right this location, right there, that slice is going to travel up a distance d, which is 7 minus y. d is equal to 7 minus y, and that's measured in meters. Okay, and the step 4 is to create the integral that gives the total work. And our basic structure for our work integral is to do force times distance and then integrate. So in our case here, the force of the slice was 29,400 dy, that's measured in newtons, times the distance that the slice travels, which is 7 minus y, that's measured in meters. So we have a newton times meter producing a work unit, which would be newton meters or joules. And that's just one slice. Now we want to add up all the slices from the different heights. But you want to integrate between the height where the first slice is, which is at y equals 0, up to the height where the final slice is, and that's y equals 4. Keep in mind that because this container was full of liquid, then the liquid is sliced all the way from 0 to 4. What if it was only partially full? What if the image looked only like this? If that was the case, then your slicing would only go from 0 up until wherever the liquid ends. Another thing is, even though the dy plays a role in constructing the weight here, the convention then is to move the dy over to this side. And now we have our integral that we could type in to Desmos or some other integral calculator, and it's going to give us a total work of 588,000 newton meters or joules. Okay, and there's our first example of finding the work done pumping liquid from a container. The next example, a liquid with a weight density of 50 pounds per cubic foot. Notice the units here. So we're in the US customary system. Also notice it's called a weight density, not a mass density, which is simply telling us that this unit here is a unit of weight. Whereas in the last example, the unit was given kilograms, it was a unit of mass. The liquid with a weight density of 50 pounds per cubic foot fills a conical container with tip down that has a base with a radius of 3 feet and a height of 6 feet. We're doing like a cone with tip down. And we're saying the base is a radius of 3 feet and the height of the cone is 6 feet. Find the work done in pumping the liquid to the top of the container. Fills this container completely full of water to begin with. And let's draw our container from a side view. We're going to position it so the bottom of the container is at the origin. The radius was 3 feet and the height was 6 feet. So we're at a height here of y equals 6. And we are pumping the liquid to the top of the container. And we are going to draw an arbitrary slice through here. Now, since this is a cone and we're slicing through a cone, if you were to look at the slice at an angle, you would see a very skinny disc like this. Now, in our picture, the radius of that disc is not a constant. The discs at the bottom are smaller than the discs at the top. We know the thickness, though, is going to be the dy. So I know that the volume of this disc is going to be equal to pi r squared times dy. We want to express this, though, as a function of y, meaning that when our slice is at height y, what exactly is the volume? See if you can express r as a function of y. Well, I noticed that this curve right here, this is linear. And I know that it goes through a certain point right here. If I wanted to label that point there, it would have an x-coordinate of 3 and a y-coordinate of 6. And we also know it goes through the origin. So it should be really easy to figure out the equation of that green line in this picture. We know we can find the slope of that line. We just do rise over run. Well, the rise is 6, the run is 3, so the slope is 2. And so we know that y is equal to, so y is equal to 2x, but the r in this picture is an x-coordinate. It's a horizontal length. So I need to solve this for x and say that x is equal to y halves. This is your expression for r. And we can say that r is equal to y halves. Another way this could have been done, I could have also drawn some similar triangles. Let me draw a right triangle sitting right here. There's the r in our image above. We know this is 3, and we know that this whole amount here is 6, and this amount is y. I can use similar triangles to figure out what r is in terms of y. We could do something like this. Looking at the pink triangle, do the ratio of the legs, a leg of 3 and a leg of 6. So the shorter leg is to the longer leg as, now look at the orange smaller triangle. The shorter leg, which is r, is to the longer leg, which is y. And now I can effectively take this expression and solve it for r in terms of y. 3 over 6 is just a half and multiply by y, and so you get the same thing, that 1/2 of y is r. In other words, r is just y halves. So there's a variety of ways of doing this. So the volume of my disk in terms of y is pi times y halves squared dy, which I could square the top and bottom and say pi fourths y squared dy. And the units of this would be cubic feet. All the lengths here are measured in feet. So now I don't need to go to the mass of the disk. We can go straight to the weight because we're given a weight density. So we're using F for weight for the force. Force of the disk, or the weight of the disk, is going to be the amount that I just wrote, which is pi fourths y squared dy, and that's measured in cubic feet, times the weight density, which is 50 pounds per cubic foot. So we're going to multiply 50 times pi fourths. Well, that's going to be 50 over 4, which is 25 over 2. So you could write this as 25 pi over 2 y squared times the dy measured in pounds. Then we want to find the distance that the slice travels. If I know that the entire height here is 6, then I just need to decompose 6, right? The distance that the slice actually travels is going to be 6 minus y, and that's going to be measured in feet. Now we're ready to set up our integral. So the total work done will be, well, the slice that weighs 25 halves pi y squared times dy. I'm going to move the dy at the end. There are all the pieces that tell us how heavy the slice is as a function of y. Then we got to say, well, how far does that slice get lifted? Well, it gets lifted 6 minus y feet. And so now we have a work done in lifting that slice. And then we do the work for all the slices, where the first slice starts at y equals 0, and the final slice is at y equals 6, because the container was full to begin with. And this becomes our integral. And when you integrate this one here, 4,241.15 approximately, and the units here would be foot-pounds. Water partially fills a conical container with tip up this time that has a base with diameter 10, so the diameter is 10, and a height of 8. The original water level is only 7 feet high. Find the work done in pumping the water to a height that is 2 feet above the tip of the conical container. So this time we have a triangle with tip up. I'm going to draw the axes. The water level doesn't go all the way to the top, so that's important. Well, we know that the tip is at y equals 8. I do know I want to pump all the liquid to a height that's 2 feet, so we have y is equal to 10, right, to go to 2 feet above the tip of the conical container. We know that the water level only goes up to a height of 7 to begin with. The diameter of the base is 10, so I know the radius. That amount is 5 feet. Notice this one gives us no weight density or mass density, but it does tell us that it's water. So that's something we're actually going to be able to look up. The other ones didn't say they're water, they're just different liquids. But water has a known weight density that we'll look up. Okay, then we have to draw an arbitrary slice. And we're going to say that it's y units above the bottom. Well, where we're pumping that slice, we're going to pump it to a height that's 10 units above the bottom. So that slice itself is going to travel only 10 minus y units. Now I can find the radius. We want to know the radius of this slice. And this slice will also be a disk. It's going to have a thickness of dy and a radius of r. And we want to express r as a function of y. In the last example, we did the green approach that you see here, which is find the equation of that line and use that to help figure out r as a function of y is. Or you could do a similar triangle approach that you see in the orange and pink. Let's do the line approach. So here's a green line right here. That's a couple points that we know that are on the line are the points 5, 0, and up here would be the point 0, 8. The rise is negative 8 and the run is 5, and the y-intercept is 8. So I know that y is equal to m, negative 8/5 x plus 8. And again, r is the x coordinate. So if I were to take this and solve it for x, I would want to subtract 8 from both sides. Multiply both sides by negative, so you write it this way, 8 minus y is equal to 8/5 of x. And now multiply both sides by the reciprocal of 8/5, which is 5/8, and that would be the x coordinate. Well, in this picture, that's also our radius. All right, so r is equal to 5/8 of 8 minus y. The volume of this disk is pi r squared dy measured in cubic feet. And then we can just replace that r with 5/8 of 8 minus y. That's all being squared dy cubic feet. And if you want, you could square the 5/8, 25 pi 64ths times 8 minus y. That's being squared dy cubic feet. But now we have to figure out the weight of the slice is going to be its volume times how heavy water is per cubic foot. Google tells us that water weighs about 62.5 pounds per cubic foot. So all I have to do is multiply this by 62.5 and I will have the weight of the disk. Now we're ready to set up the work integral. So there's our weight, and we have to multiply that weight by the distance that the slice travels, 10 minus y in here as well, and I'm going to move the dy to the end of the integral, 10 minus y right there. So now we have a product that was a weight times a distance. So we have a work, and then we want to add up all the works. We're going to start where the lowest slice was when y equals 0, and the final slice was not 8, right, because this container wasn't full to begin with. The final slice occurred when height was 7. And then when you type in this integral into a integral calculator, you get 28,634.3, and the units here were foot-pounds. Okay, so this is our final problem for this lecture on pumping liquid from a container.